Good morning, good morning. Thank you for coming. My name is Milos. I work for the Ethereum Foundation protocol prototyping team, and today I will talk about Glamsterdam. Who here knows what I mean when I say Glamsterdam? Raise your hand. And who has no idea what I'm talking about when I say Glamsterdam? Okay, so good. Let's first see what I mean by that and what am I even talking about. So on Ethereum, you probably know we have hard forks every couple of months, every year, sometimes twice a year. And those forks basically introduce upgrades to the core Ethereum protocol, and we get some new cool features on the protocol level. And this is historically, uh, 2 forks ago, we had Pectra, and I will explain how we came up to the names. They are slightly here. So on the Ethereum, we have 2 layers. We have execution layer and consensus layer. And uh, we started after the move to the proof of stake. When we introduced consensus layer, we started making forks both on execution layer, consensus layer at the same time on the same date. And we started, but they are sort of slightly different technologies. And we started basically the names of the cities like Prague, Osaka, Amsterdam, Bogota. They are names of the forks that happen on the execution layer. And Electra, Fulu, Gloas, Heze, those are the names of the star in the universe. And we named those for the consensus layer. So we basically use this ideology to combine the cities on the earth and the stars in the universe to kind of like bridge the gap. And the name of the fork is combined those two names together. So for Electra and Prague, that was Spectra, and you can see the others. And these are the previous forks. So very briefly, in Spectrum, that happened in 2025 in May, we gained these features. We unlock some account abstraction, which enabled better wallet UX. We allow validators to consolidate. Before Pectra, you could only run a validator node. You needed 32 ETH. If you had 32,000 ETH, you needed 32,000 validators. So now with validator consolidation, you can have like run one node that has more ETH on its own balance. So its own vote will give more votes to the consensus system. And we draw address exits. This is a bit more technical. But basically it allowed validators to exit the validation directly from the executions layer instead of always going through the consensus layer. In Fusaka, we focused on scaling L1 and L2. Around that time, we increased the gas limit on L1 from 30 million gas per block to 60 million gas per block. We also unlock some passkeys for wallets and other primitives that they can use more natively with precompiles that support different cryptographic primitives. And the main focus on Glamsterdam will be L1 scaling, reducing trust assumption between the builders and the actual validators, and some gas optimization, which indirectly helps with gas scaling. We will cover this very in details. And we already know what is the high-level idea for the next fork after Glamsterdam, which is Hegota, and that is censorship resistance and native account abstraction. We don't know exactly yet the dates. We expect that the Glamsterdam will happen somewhere in the third quarter of 2026, and in 2027, we will somewhere in 2027 we expect the next fork afterwards. So let's focus on Glamsterdam. So these are all improvement proposals that comes from Glamsterdam so far, and don't worry about this. All of them read. We will cover them a bit late in details, but not every single one of them. The QR code you can go to the website called Forecast, where you can see all of these improvement proposals for in details what exactly is. Go read more documentation if you really want to learn all the exact details. I will just explain what are these differences. So first, how the Ethereum core developers agree on what proposal needs to
they want to do in the next fork. So at the beginning, uh, when we discuss the fork, we first select the headliners. Those are usually one improvement on the execution side, one improvement on the consensus side, that are the biggest and the most sort of set a theme of the entire fork. Like, what do we want to focus on? And they are usually the biggest things. So for Glamsterdam, that is the two that are marked with a star, EIP 7732 and EIP 7928, enshrine proposer builder separation, or ePBS, and block level access lists, which we call BALs. So they set the themes for Glamsterdam. And after the headliners are being set, then they are called headliners, and they are considered. We are not shipping this fork until these two are done. These two are the two primary things that we want to ship. Others are a bit more optional. Then they go and discuss what other things we want to add in the same fork, either because they are small and they are nice improvements, or because they somehow depend on interact with the headliners in some way, or to the general theme, or something like that. And again, depending on the complexity and everything, something that is maybe very good, but if it's too complex, we are not going to do it in the same fork. We will maybe make it a headliner in the next fork, etc. And first, all of the EIPs, EIP stands for Ethereum Improvement Proposal. All the EIPs go to the stage of consider for inclusion, where we basically consider everything. And then maybe through voting, some of them are no longer considered and then they're declined for inclusion. And none of the declined ones are showed here. And as clients team starts working on something, once they make enough progress and they maybe run it to a DevNet or something like that, then when we feel very confident those are ready and we are most likely going to ship them, then we upgrade them to schedule for inclusion status. And those are all the ones that are being bold in a bold font. So all of the bolded ones are pretty much guarantees to be included. Everything else we still plan to include. But if, for example, all headliners are all done and ready, and maybe a couple of the others that are not done, we might decide we don't want to delay the fork for some of the others, non-headliners, if they didn't make it in time because people or engineers didn't have time to prioritize them and work on them, or we figure out they might be too much effort, or there are some other difficulties with them. We are completely fine with removing some of those. It's also possible later to add one or two more forks proposals, because something very small or something that needs to be improved comes up to the last minute, but that rarely happens. So let's talk about the headliners first, because again, that sets the theme of the entire fork. Enshrine proposer builder separation. So does anybody here know what are the role of validators, or sort of like, does anybody here doesn't have any clue how the consensus mechanism works on Ethereum? Feel free to raise your hand so I just know how much in details I should go on that topic. Okay, so I will assume everybody has at least some knowledge. I will very briefly say, so validators are in charge of verifying the blocks. Every slot or every 12 seconds, one of the validators is being selected to be a proposer. So they are by protocol supposed to build a block and then send it to the rest of the network. There's the validators, they validate and vote whether the block is valid. And at the end, they come to a consensus that the block is valid, and then the next validator will build on top of the last block, and the blockchain keeps building. So I did say that slot is 12 seconds, and you will see later that I say that broadcast and execution time from 2 seconds to 9 seconds changes with this change. So even though the slot is 12 seconds, the first 4 seconds are reserved for block building, propagation, and validation. Then the next 4 seconds are reserved for validators voting on those votes. And then the last 4 seconds are reserved for aggregating those votes and propagating to the rest of to the entire set of validators. I'm not going to go into details, but usually the entire time that the validators have to propagate the block through the network and verify it is around 2 to 4 seconds on average. And with this proposal, what we do is So yes, another thing to mention, currently protocol is designed such that every validator builds their own block. But we have uh, out of protocol entities, core builders and relays in the middle, who are trusted entities, and most of the time they are the ones doing the block building because they are more sophisticated builder. They can extract MEV, make some profit, and they share part of that profit with the actual proposers. But this is done outside the protocol. And in order to make it safe, there is relays, which are a bit more centralized, and they are trusted entities both by the proposers and both by the builders. Um, and they make sure that everybody basically trusts the relays in this system. And it's not part of the protocol. You have trust assumptions. So enshrined proposer builder separation is designed to make the builders first class citizen of the protocol as well. So now we have another entity that is just responsible for building the blocks. In short, how it works, um, the bids for who is going to build the block is different from who is going to propose the block. The block proposer has a right to still build the block themselves, but alternatively, on the protocol level, they can also accept the bids, and they can accept the bid from any of the builders, and they can say, okay, and then they propagate on the network, on the protocol, that this builder is going to reveal the block that they built, and the builder still has to pay the price to the proposer, even if they don't reveal the block, even if they don't build the block. So there are some guarantees there expected that now basically replace the relays. Um, I'm not going to go into details. You can scan the QR code. You can read all about it. It's very complex change. It's one of the reasons why the fork takes a bit longer to implement, because there are a lot of moving parts, a lot of external entities, meaning builders and relays, that also are affected by this. So we have to coordinate with them and figure out how best to do this. But the main benefits is that now we no longer have trusted entities. So we reduce the trust assumption in the whole protocol. And because of how we structure the fork, um, how we structure the proposer process and when the block is being propagated and by who and when it's being verified, we get significantly more time to propagate and verify block now than in a previous design. Um, the next headliner is block access list, or BALS. Um, Currently, so this doesn't help with block building, but it significantly helps with verifying the blocks. So currently, if you want to execute and verify the block on execution layer, you have to run every transaction in order, and every transaction runs purely sequentially. So you start executing the transaction. Then, for example, you have something to read from the state, then you stop executing, you go to the hard disk, you read the state, you get your state, you continue executing, again, read something from the state, you stop executing, etc. So there is a big sequential execution that is interrupted by using disk to read state, and again write state, though you can write state sort of in parallel later on. That's not on a critical path. And after you execute all transactions, you have to calculate the new state root after all the transactions are being executed. The block access list, in short, gives us a snippet of what are all the states that are being read in a block and what are all the writes that are being written during every transaction. What that allows us is, as soon as you receive a block and block access list, you can start prefetching all of the states that will be ever read in the entire block. And you can, since you know all of the writes that are going to be done in parallel, you can start calculating state root already from the beginning without executing any transaction. So you can start reading everything from the disk. You can start calculating state root from the beginning, and all transactions, because you know what changes in each transaction, you can execute transactions in parallel. So you can execute transaction 5 without first execute transaction 1, 2, 3, 4. You just know what state changed in those transactions, and that's enough for you to execute and verify transaction 5. So eventually, once you execute all of that, you have to make sure that what block access list says that was modifying transaction 2 actually did get modified in transaction 2, etc. So you basically can parallelize the execution, you can prefetch everything from the state, and you parallelize calculating the state root, which significantly improves the speed of we can verify the block. Again, you can scan the QR code, you can read all the details, but yeah, it gets significant improvements on the verification speed of the block. As I said, it doesn't help with the block building, but it helps with the block verification logic. Um, Again, these are now I'm going to talk about other improvements that we could, and I separate it into multiple categories that are sort of related to each other. One is gas repricing, which is basically focused around scaling L1, which is also what block access lists do. They allow us to execute the block faster, meaning verify blocks faster. But we want some other things. If we want to increase the gas limit, we run into multiple challenges on a protocol level. So one of the challenge is if you increase the gas limit, let's say 5 times, somebody, if you keep everything the same, somebody can make the block 5 times bigger in pure bytes size. And that can make it, in a worst case, it would take 5 times longer to propagate through the network. And that comes with its own challenges. So maybe execution logic is 5 times faster, so you can compensate execution verification logic with BALs, because BALs you can parallelize based on how many cores you have. But if it takes 5 times longer to propagate to the network, you still run into some bottlenecks. So for example, increasing the cold data floor cost, that basically increases how expensive is the cold data. And the more bytes you add using the cold data, the bigger the transaction is, the bigger the block is, and we want to price that more accordingly to what we want to achieve. Another issue with when you increase the block gas limit is um, the rate at which the entire state grows will also increase. So if you suddenly have 5 times more gas and there are 5 times more transactions on Ethereum, the entire state of the entire Ethereum will keep increasing at a 5x rate compared to the current state. So that is an issue, because for most node operators and for most home operators, we advocated that 2 terabytes will be enough to run Ethereum node. We know that the state keeps growing and always keep growing, and we need some solution in the long term of how that can be sustainable. But the 2 terabytes gas limit is not something we would hit very soon. But if we scale the gas limit 10x, and the state we will hit that boundary 10 times faster. So instead of maybe having 10 years to figure out the state growth problem, now we have 1 year to figure that out. So the state growth is another problem that we can run into if we suddenly increase the gas limit significantly. And that's, for example, what the state creation gas dose increase is focused on, and the state access gas dose update, because as the state grows, it takes longer to read stuff from the disk. It takes longer to write stuff to the disk and update the state route, etc. So there are other stuff that's regards to state that change as the state grows on its own. The first one is reducing intrinsic transaction gas. Is very interesting, and I think maybe the most important for average user out of this list. Currently, if you want to send the ETH, simple ETH transfer from one account to another, always costs 21,000 gas. But if you think about it, if you send your ETH to account that already exists in a database or in a Ethereum state, that is just changing one number to another. Like there's no new state creation, anything like that. It just changes one number to another, just the balance changed. If you are sending it to an address that doesn't already exist, we have to create a completely new account on the Ethereum state that will now have the thing. So there is a increase in the size of the entire state, and it should be priced differently. And that's what this is going to do. Basically, if you're sending to already existing account, it's going to be cheaper than 21,000 gas. If you're sending to and creating completely new account, it's going to be, I think, similar prices it is now. But the sending ETH transfer, simple ETH transfer to already existing account is going to become cheaper. I think some other stuff are going to become cheaper. Like, for example, the 21,000 gas is initial gas that you pay just for interacting with the account, like a smart contract, even if it exists. I think that is also become cheaper because you're not creating anything in that first initial interaction. But then again, how much smart contract logic you consume. That's going to add to the gas anyway, but it may become slightly cheaper to do basic stuff. And many of others are updates and increases, basically trying to make consistent that operations and their prices are consistent with the target gas increase that we planned. We still need to do a proper benchmarking to figure out exactly how much we can increase the gas limit. Current target, I believe, is 200 million. So we plan after Glamsterdam to scale from 60 million to 200 million gas and see how that whole goes. Maybe we can even bump it further. But that would be like 3 times increase in a couple of months from now. EVM improvements. These are mostly some stuff that help developers, the app developers. ETH transfer and burns emits log. Basically, now, if you look through the receipts of the block called transaction, you can find, for example, ERC20 transfers. They will all be shown in a nice logs. But if you want to see ETH transfers, because they are on a core protocol, they were never emitting the logs. So you never see them as logs. There are some metadata you can go and trace and figure it out, but it's much harder to do that. So this proposal will actually emit the log every time the ETH is transferred between two accounts, because it becomes much easier for wallets, aggregators, whatever, to figure out what ETH was transferred during the transaction between what accounts. Slot num opcode. Currently, the EVM, you don't have direct access to what is the current slot. You can technically figure it out because you know what is the time step of the block, and then you can do some math and figure out what is the slot number. But many applications would benefit and simplify significantly if they would know slot number. There is no reason why we shouldn't support that. Increase maximum contract size. This is something that developers were asking for a while. The 24 kilobyte is very small. It's been like that, I think, since very beginning of Ethereum. Maybe not since very beginning, but at least for the last 8 years or something, I believe. And smart contract developers have to figure out to split their code into multiple smart contracts that they're going to call between themselves, etc. This is not a huge increase, but there are many challenges in going further than that. We have plans for that, which might happen in a fork afterwards, or maybe 2 forks from now. They are more complicated, and we want to do something as a first step to make it life easier, and we are going to do a proper solution later down the road. Deterministic factory pre-deploys. This is yet another nice feature, so that basically make it consistent. If you want to deploy on the same address across Ethereum layer 1 and some layer 2s, and you want always to be sure that you always deploy on the same address, so that users don't have to worry about, am I on base, or am I on Arbitrum, and am I on layer 1? Where am I? What is the address of my application or DEX or whatever, or the ERC20 token? This will allow the developers to always be in control, or always be consistent on what addresses they deploy their smart contracts, regardless of what layer 1 or layer 2 they are on. Backward compatible functions. This is more like Solidity improvement stuff. Most developers will not touch this directly, but Solidity will offer certain features and make certain operation cheaper in the terms of gas, how much it would cost to do some operation in the background. It's more for like language programmers to care about, rather than the app developers. Consensus improvements, as I said, ePBS, the first headliner that I covered, is on the consensus side, and most of the consensus work took a bit longer for that. So none of this, as you see, is bold. So none of this is actually being done so far. We still plan to do them. Very short, what is the most important from this list? Yeah, the first one is purely security oriented stuff. If somebody gets slashed, we don't want to let them propose in the future, which completely makes sense. Should be part of the maybe things from the beginning. The last one helps with propagating. Currently, if you if you're propagating blobs on the network, you propagate columns from all blocks at once, but it can happen that the recipient has already parts of that columns, and this allows to propagate only the parts that they are missing in a way. So optimization, you don't propagate data that the other side already has in a way. Um, just network optimization stuff on the protocol level. The middle two are similar and related. Basically, it will be, if you are a validator and you want to stop being a validator, it should be faster. Like it will take less time um, to exit validation if you want to exit. And the exits and consolidation is if you own 10 validators, is it having 32 ETH, and you want to combine them into one validator, that's called consolidation. Exit is if you want to stop being validator. Now technically they're going to be processed kind of together in order. They're going to be one queue for processing all of that, and it's going to be faster than before. Um, Slight optimization for validators so they can faster stop being validators or consolidate them, etc. And the last category is a bit of code health and tech cleanup on the protocol level. It's more for the core developer improvements rather than end users or even validators, etc. Let me see anything highlight. It's mostly just making things more performant and better. Yeah, I don't think there is anything here for most of the audience. Like for core developers, these features matters because they allow us to simplify protocol, to simplify the code, to remove some of the functionality that is not being used, to make some stuff more performant on either networking layer, like the sparse blob pool. The E70, E71, basically they work together with the block access list. They are sort of dependent. They are related of how the clients sync, because until now the client didn't have access. We didn't have block access lists, but now we are also adding them during the sync process when you just start a new client. So that also like supports in that regard. It's not necessarily needed, but it improves things, and syncing should be much faster and more consistent. It's mostly improves the life and the quality of the clients themselves. I can dig deeper into this during the Q&A if somebody has any specific topic, either from this list or any of the previous ones. So in short, the Glamsterdam upgrade is focused on scaling L1 and reducing the trust assumptions primarily on the relays and the builders, because they are now part of the protocol. And let's very quickly look at Hagota, which is the fork after the Glamsterdam, probably coming somewhere in 2027. The one main thing that is already selected as a headliner is Fossil, which is fork choice inclusion lists. In short, this allows this recognizes another entities of part of the consensus protocol that are called includers, and they, even though they are not building a block or proposing the block, they can force the next proposer and builder, by extent, to include certain transactions in the block themselves. So they basically say like, we want these transactions to be, or more like, if I'm includer, I would say I want these transactions to be included in the next block. Now, it's not very strict. You cannot fully force the builder to do that. The builder will be forced to do that if they still have some gas limits left in a block. Like if they want some transaction that they want to include, they have that freedom. But if there is an extra gas limit that they can use, and there are some transactions that other people want to include via inclusion lists, then they are forced to include them. But if they have a full block, then they can do a full block and ignore the inclusion list. So it's a sort of a compromise with builders having a freedom to do what they want, but also respecting wishes of other participants of the network that can force them to include something that maybe they don't want, or maybe they don't know about certain transactions, etc. But yes, basically it's helped with censorship resistance, because if we have builders that don't want to include certain transactions for censorship reasons, this way they will basically be forced to include them. Again, if their block is not full, they will be forced to include them. And another proposal, which is not a headliner, this time for Hegota was a bit difficult to select a headliner, because none of the options was so big or important. The only one that was strongly considered was frame transactions, but some client teams, due to pure complexity of the change, weren't sure this is the best path forward. They definitely want to do something regarding native account abstraction, which is what frame transactions do. They definitely want to do something regarding post-quantum security on the account level, which is something that frame transaction can do. But whether the frame transaction design and the actual specification of how we achieve that is the right approach, they didn't want to commit to be a headliner status. So it's the only one that is being considered for inclusion at the moment, and there's more research on that to decide if there is a if this is the right approach, or do we want something else to consider. And so far, these are the only two proposals that are being scheduled or planned for the inclusion. And currently, we are in a period where all other EAPs are being proposed and being discussed. What else is going to be there, while we still work on the Glamsterdam, so it takes a bit longer. But in short, for Hegota, we get censorship resistant through fossil, and we will get some post-quantum security for the externally owned accounts, and we will hopefully get some native account abstraction support as well.